All right, so the last two things that we have to talk about with this chapter concern temperature and catalysts. And we'll probably spend more time with the first rather than the second, because really the only thing that a catalyst does is it disrupts the mechanism and causes the mechanism to go faster by making the rate determining step faster. But for temperature, it's a little bit more complicated. We know just as a general rule, increase the temperature, that increases the reaction rate. And we know that that has a lot to do with just the idea in general that you need sufficient energy to get the reaction to kickstart anyway. So for certain temperatures, the activation energy is just too much to overcome. And so it never happens at that temperature. And if we look at just kind of a diagram like this, we can see that really that threshold energy that we have to overcome, we're not going to get a consistent reaction. We're not going to get any reaction at all for that matter until that threshold energy has been crossed. And so obviously the higher the temperature is, the greater chance that we are going to get of crossing that threshold energy and getting to, at least from an energy standpoint, a proper collision. Now, we still have to worry about the orientation part, but at the very least, we will have crossed the energy barrier. And so we covered this kind of at the beginning when we were looking at the reactions between ozone, or just in general, kind of talking about collision theory, the idea that orientation does in fact matter. But now we need to talk about from an energy standpoint. Let's say that we have two collisions about to occur that do have the proper orientation. The proper orientation being we've got this ozone molecule that's about to collide side on with the nitrogen to hopefully make nitrogen trioxide, which is what we're trying to do. Well, in the first case, even though we have proper orientation, because we don't have enough energy, the collision is ineffective and it does not proceed to make the products, or in this case, the intermediate and the product. So we've got to do a little bit better. We've got to do a little bit more. When we have sufficient energy, the sufficient energy of that collision will allow the reaction to take place, and we end up getting product molecules, or in this case, product in the form of oxygen and intermediate in the form of nitrogen trioxide. The nitrogen trioxide can then go on as an intermediate, react in a separate step to ultimately form the dinitrogen pentoxide, which is the product of this reaction. So the whole idea of temperature and energy is very, very closely aligned. And what we can see here is in this diagram, we're basically showing this dotted line here represents the threshold energy. And these graphs individually represent the number of particles that have that particular energy. And so we can see that if we run this reaction at 298 Kelvin, basically room temperature, 25 Celsius, that we will get a fraction of them that will meet that threshold energy, but the majority of the molecules actually are not energetic enough to overcome the activation energy. But if we increase the temperature, even by 22 degrees, now we are at 47 Kelvin, or excuse me, 47 Celsius instead of 25. What we will see is that a majority of the molecules are going to shift toward having more energy because higher temperature means higher energy. And the number of molecules that now have the correct energy, or at least can overcome that threshold activation energy, is considerably higher. And so with this information, we can actually start to make a quantifiable relationship between the temperature at which we run a reaction and the rate constant for that reaction itself. And the relationship here is given to us in the form of what is called the Arrhenius equation. The Arrhenius equation allows us to calculate the value of the rate constant at any given temperature in Kelvin. So this particular graph shows it in degrees Celsius. In order to use the Arrhenius equation, we usually end up talking Kelvin. And what we can see is that the relationship here is an exponential one. An exponential in the terms of we've got this term A here that don't really fully understand, at least not now. And this exponential term gives us activation energy, gives us the universal gas constant R, gives us temperature, but it's all tied into the exponent of that base unit E. So it's an exponential graph. Now, one thing about exponential graphs, they're not exactly easy to manipulate. You've got to do some pretty heavy trigonometry or even calculus if you want to pull out terms and look at activation energy or temperature instead of looking at K if you're trying to solve backwards. Not the easiest thing to do. It would be much easier if this reaction were linear, where we could look at this equation, plug it up to some sort of slope-intercept form, and be able to interpret the slope and the intercept and the value of y and x. And that's what this does. So by getting rid of the e term and applying natural log, we can take that exponential and turn it into a straight line, a linear equation. And the linear equation has, I'm going to rewrite it here, natural log of k is equal to negative EA over R times 1 over T plus the natural log of A. This is our slope-intercept form where the natural log of K is Y, negative EA over R is the slope, 1 over temperature is the X, and the intercept is the natural log of A. So if I take a plot of natural log of X versus 1 over Kelvin temperature, the resulting graph is this Arrhenius graph like this. And from this Arrhenius plot, we can get some really important information. One of the things that we can get from this is by manipulating the slope, we can actually estimate, calculate the activation energy for the reaction. After all, the slope is just the opposite of activation energy over R. And R in this case is a form of the universal gas constant, 8.314 joules per mole times Kelvin. That's why temperature has to be in Kelvin, because of the value of this gas constant. So if I take my slope and multiply it by the opposite of 8.314, I will get the activation energy for the reaction in joules per mole. Gives me a little bit of insight in terms of, well, how big is that energy hill that I have to overcome? The other major contributor here is I can calculate the intercept, and the intercept is equal to the natural log of A. What is A? A is something called the frequency factor. Frequency factor is kind of loosely related to reaction speed. The higher the value of that frequency factor, generally speaking, the faster the reaction. But what this equation also can do is it does establish for us a relationship between X and Y, temperature and rate constant, where it would take a little bit of manipulating to do. It would certainly be better if I had this graphed in Excel, but I could take any value of temperature, use that equation, and figure out what the rate constant should be, provided I know everything else. And so if you have the data, obviously you can do that with the equation of the line, but there's a variant of this equation that we can use. It's called the dual form of the equation, where I can manipulate basically that component of it. And what happens is the A terms kind of get canceled out in the wash. And using either form here on the bottom, the only difference between the two is, in order to get rid of the negative sign on the slope there, we switched the order of subtraction in the parentheses. But either way that we look at it, if I am just looking at two reaction scenarios, I do the reaction at this temperature and here's its rate constant. I do the reaction at this temperature and here's its rate constant. I can use the dual form here to calculate the activation energy based off of what's left. Or if I know the activation energy and I know some of my data, I can figure out what temperature it would run to get a rate constant of this. Or, here's my data for 200 Kelvin. What's the rate constant at 400 Kelvin if activation energy is equal to this? So this becomes a relatively simple way to algebraically calculate and move from one to another. And so we will see this kind of thing in action in both ways. I can tell you right now, the quiz is going to have an Arrhenius equation question on it. It is not going to have an Arrhenius question where you have to do graphing, but rather it's going to have an Arrhenius equation where you're going to be using something like the dual form here to either calculate activation energy or to calculate, given one set of conditions, calculate for another set of conditions, that kind of problem. And so if you look in the homework that is due this evening, those are the kinds of problems that you're going to see. Now, you're also going to see, more so in lab, you're going to see questions like this one, where we have to do some graphing of data and do some calculations for activation energy and frequency off of that data calculation. So I would invite you again, open up Excel if you have it available and open to you. So our question here was, we need to determine the activation energy and the frequency factor for this reaction where chlorine monoxide is reacting with itself to make chlorine and oxygen. And so we need to input our temperature data. Temperature data are in Kelvin. And we've got 238, 258, 278, 298. Those. And our rate constants in per molar per second. So what kind of order is this reaction if the rate constant's in per molar per second? What's the overall order of this reaction? It's second. So remember, we're starting with molar at 0. We divide by molar for every order. So molar to the first, 0 order. Molar to the 0th, first order. Molar to the negative first, second order. So since this is molar to the negative first, this is a second order reaction. We would draw reaction mechanisms based on this being a second order reactant in terms of chlorine monoxide. Okay, 1.9 times 10 to the 9th, 3.1 times 10 to the 9th, 4.9 times 10 to the 9th, 7.2 times 10 to the 9th. Okay, now the other thing this should tell us, our rate constants here are extremely high. This is a fast reaction. Now to make an Arrhenius plot, we don't want to just simply make a scatter plot off of this. The scatter plot we get is going to be curved and incorrect. We're making Arrhenius plot. So for an Arrhenius plot, we need 1 over temperature for x, and we need natural log of k for y. So for that, 1 over the temperature, and then copy, paste. For natural log equals natural log of k, and then copy, paste. This is the plot that we need to make, and it should come out linear. Now, if you're doing this in Excel, Excel does not automatically rescale it for you. You'll have to do that yourself. If you're doing this in Sheets, Sheets does rescale it usually. We rescale it, comes out a lot nicer. Need to add a trend line. And we want the equation of that line in particular. R squared tells us it's pretty linear. Okay. So with the data that are in front of us, we now can see that our slope is equal to negative 1579.8. To find activation energy is equal to the opposite of R times the slope. So negative 8.314 times 1579.8. All of our data here is to 3 sig figs, so or 2 sig figs rather for K, so let's keep it that way. It would be positive 13,000, and the unit here would be joules per mole. So our activation energy is 13,000 joules per mole. That sounds like a lot. It's really not that much. It's 13 kilojoules. And when you consider how fast this reaction is based off its rate constants, that small value for activation energy makes a ton of sense. Okay, so that's the slope part for the intercept, for the frequency factor. $27.994 is the value. Natural log of A is equal to that. To get rid of the natural logs, we have to raise each side to E. So A is equal to E to the 27.994. We get 1.4 times 10 to the 12th. Frequency factor does not have units. So if we're asked in lab or in your homework to do any kind of graphical analysis with Arrhenius equation or any kind of linear plot like that, this is what you have to do. Throw it into your favorite spreadsheet graphing program, get the graph, find the equation on the line, And then based on what you're asked to do, you can interpret the data from there. So you can find activation energy through the slope. You can find frequency factor through the intercept, or you can use the equation of the line to calculate X or Y if you're given. So if we wanted to figure out, let's just say for the sake of argument, if we were asked to do a question like this, here's our previous graph. What is the value of the rate constant at 125 Kelvin? Well, we could use this equation to answer that question. What we would have to remember, though, is that X is 1 over T, and Y is natural log of K. So I can't just put in 125 in for X, solve for Y, and that be the correct answer. I've got to manipulate it. So since we're at 125, that means that X is equal to 1 over 125. So we're talking 8 times 10 to the negative third. And if I plug that in, Y is equal to negative 1579.8 times 8 times 10 to the negative third plus 27.994. I can do that calculation. And I will get 15.4. But 15.4 is not my value of K. Remember, Y is the natural log of K. To get rid of the natural log, I got to take everything to the E power. So K is equal to E to the 15.4. 4.7 times 10 to the 7th. And since we know that this is second order, per molar per second would be the unit. So if I have the graph, I can use the graph to calculate one direction or the other. If I'm given some set of conditions or a rate constant, I can figure out the temperature. But I have to remember that the graph has been manipulated. X is not just simply X, it's 1 over temperature. Y is not simply the rate constant, it's the natural log of the rate constant. So I would have to bake that into my calculations. And if this sounds kind of familiar, when we first started doing graphical analysis in Chem 105 lab, this was the kind of stuff that we were asking you to do for some of the more challenging problems in that assignment, when X wasn't really a variable and Y wasn't really a variable, but rather a function or a calculation. All right. Any questions with this? Are we on the same page? All right, then let's talk about the last thing catalysis, surface area. Now, based on our collision theory, this first sentence should make a lot of sense. If we increase the reaction surface area, the rate of reaction is going to come up as well. The more collisions that we can make, the more likely that those collisions will be good and therefore fruitful, making reactants into products. What catalysts do is catalysts will lower the activation energy of our reaction, and they'll do so in one of two ways. They'll either help with orientation, or, and that's usually what happens on a lot of surface catalysts. So take, for example, the catalytic converter in your car. The way that it works, the way that it is helpful is that platinum catalytic converter gives a place for the molecules of gas to rest on, so that when that extra oxygen comes in, it's able to interact with the carbon monoxide at the proper orientation and turn it into carbon dioxide, which is a whole lot safer. And so the whole idea of that platinum surface is giving us a place to basically hold one of the reactants in the right orientation so that the other one can come in and do the reaction. So that's one way that a catalyst works. Another thing that catalysts do is they often introduce a secondary mechanism, and that secondary mechanism has a lower activation energy than the original one does. And so in both ways, either by increasing the number of proper collisions, by creating a better surface, or by changing the activation energy and lowering the energy barrier so that you don't need to run it as nearly as hot of a temperature, we can increase the reaction speed in that way. Now, two types of catalysts. Homogeneous catalysts, these are catalysts that are in the same phase as the reaction. You're about to do a reaction in the lab where we're going to do everything in solution, and we're going to introduce a homogeneous catalyst in that to show how catalysts will impact the speed of that reaction. Same phase. Usually that is the better of the two options, because since they are already in the same phase, the catalyst is automatically going to find whatever it is that it reacts to, lower the activation energy, the reaction runs faster. Heterogeneous catalysts, obviously, those are in different phases. This is the catalytic converter example. Solid platinum surface to help assist gas phase reactions. And so there is a limitation there. You can only have reactions taking place on the surface of the catalyst. So if the catalyst is not in the middle of the exhaust manifold, you got to wait for those molecules to make their way to the catalytic converter in order for the reaction to be sped up. Some other things that we want to be on the lookout for as far as catalysts go. First of all, they do not appear in the overall chemical equation. So even though they participate in the reaction and they will show up in reaction mechanisms, you can think of them almost as the opposite of intermediates in terms of their interference and their appearance in the mechanism. Intermediates show up as a product and then later get used as a reactant. Catalysts are the opposite. They will usually show up as a reactant and then be given back to us in a subsequent product step. And so in the process, the catalyst does not get used up. You don't have to go to the body shop to periodically add more platinum to your catalytic converter. It's going to maintain the entire time. The only thing that might happen to it might get fouled up occasionally, and you gotta clean it or replace it. But that's usually in more extreme kinds of circumstances. Otherwise, the same thing basically will run you for the life of the car. Catalysts can be used many times over before losing efficacy, before losing their effectiveness. They're usually used on very early in the mechanism and have an impact on the rate determining step as a result. They do not change anything related to the enthalpy. So we don't see them changing the overall heat energy differential between reactants and products, just the activation energy differential. When they react, if they react in a reversible step, they are going to impact the reversible step equally. Again, what you have to think about is they're only impacting the activation energy. So the activation energy shrinks. It'll shrink in both directions. And like I said before, we usually see a different mechanism coming on as a result of the catalyst being present compared to if it were not present. So graphically, what does it look like? Well, if all it's doing is changing the activation energy in a single step reaction, we would see just that the activation energy is lowered. If it introduces a different mechanism, what we'll see is that that different mechanism will have a net change where we can see the activation energy is considerably smaller through the series of steps, but the overall change in energy, our delta H, is not going to be impacted. Regardless of whether we are using a catalyzed or uncatalyzed reaction, delta H does not change. It's going to be the same regardless. Now, just as a side note on kind of where else can we see these besides, cars or different kinds of chemical reactions, enzymes are probably the most common thing. Enzymatic activity inside of biological systems are basically a biochemical catalyst process where the enzyme is able to come in, it is able to bind to the reacting species through its active site and is able to help generate the required products through a simpler, less energetic means because, kind of like a surface catalyst, the molecules are already there, they've already been set. The enzyme basically helps to get the reaction to happen easier. Now, I mentioned before about catalytic converters. Those are heterogeneous. Your book's being a little bit generic here. It's usually platinum. Sometimes it's palladium, but it's usually some kind of inert metal because we don't want something like iron in there where iron is going to react with those gases as they pass through, and we obviously don't want that. So that is it for kinetics. Like I said, I told you it was going to be mostly shaded toward the temperature part. The Arrhenius equation is kind of the big deal there. For catalysts, we just need to know a few things about them to kind of rationalize how they work and what they do to make the reaction go faster. Does anybody have any questions before we call it a day here for lecture? All right, so then what we're looking at is for class tomorrow, we will be starting into equilibrium. After our first equilibrium lecture, we will get into reviewing for the kinetics quiz. The kinetics quiz will be on Wednesday morning. And so we will be preparing for that by doing the kinetics skill builder after lecture. And then obviously in active, you've got the bonus assignment to give you some more practice further from there.